The Voyager 2 spacecraft has finally bid farewell to our solar system. Voyager 1 and 2 were built in the 70s to explore the gas giants to the outer edges of the solar system. Voyager 2 just revealed a terrifying discovery and shocks the entire world. The initial signals arrived as mere blips in a sea of data indistinguishable from the background noise that the spacecraft has transmitted since crossing into interstellar space. Then the patterns began to emerge. A sequence of high-energy particle readings so anomalous in their intensity and rhythm that even veteran mission scientists felt a chill run down their spines. Instruments calibrated for decades, suddenly registering bursts of radiation unlike anything recorded before. Those bursts persisted, growing stronger with each passing transmission window, carrying within them a message of cosmic scale and unfathomable consequence. Before we start, smash the like and subscribe buttons for more updates. At first, it was dismissed as a sensor malfunction. Voyager 2's systems, after more than 4 decades of operation, are prone to glitches. A team at the telemetry center pored over logs comparing data streams against redundant channels. They initiated diagnostic protocols, rerouted power through backup systems, adjusted antenna orientation to rule out interference. Every technical anomaly was cross-checked and eliminated. Yet, the readings persisted. Sharp spikes of charged particles with an energy signature that suggested origin both near and impossibly distant at once. Something out there was awakening. As the realization set in that the readings were genuine, discussions escalated beyond engineering wings and operations floors. Planetary scientists weighed in, noting that the intensity of these particles exceeded anything Voyager 2 had encountered near Neptune or in the helipause. Astrophysicists pointed out that the spectral distribution of the particles hinted at processes far more violent than typical solar flares or supernova remnants. A new phenomenon appeared to be at play, one that defied current models of interstellar physics. Somewhere along Voyager 2's silent journey, it had stumbled upon something the universe had kept hidden until now. The implications were staggering. If Voyager 2, drifting more than 18 billion kilometers from Earth, was detecting a source of such raw power, then that source must dwarf any known cosmic accelerator. The prospect of a previously unknown type of galactic engine capable of hurling particles across light-year with such force-sent ripples through both theoretical and observational astrophysics. Astronomers scrambled to point ground-based observatories toward the spacecraft's line of sight, while space-based telescopes reprogrammed their surveys in hopes of capturing a visual counterpart to the invisible storm. All eyes turned toward an invisible threat growing in the void. Yet, there was something far more unsettling than mere scientific excitement. The readings carried within them a structure, an almost rhythmic modulation that suggested intelligence or design. Intricate oscillations interwoven with chaotic spikes, as if the very fabric of space-time was being twisted and molded by an unseen hand. Could it be a natural phenomenon, so strange it mimicked artificiality? Or was there truly an intelligence behind it? The idea that Voyager 2 might have tapped into a cosmic beacon, one broadcasting signals with malevolent purpose, filled researchers with both fascination and dread. Back on Earth, theories proliferated. Some speculated that a dormant interstellar object, perhaps a relic of an ancient civilization, had finally crossed Voyager 2's path. Others floated the more terrifying hypothesis that a dying star was collapsing into a black hole with unprecedented ferocity, its singularity wringing space-seam until weird quantum effects spilled outward in unpredictable patterns. If such a cataclysm were underway, would the wave of high-energy particles eventually reach our solar system? Would Earth's magnetosphere withstand the onslaught? Or might our own planet's delicate shield buckle under a cosmic hammer blow? Philosophers and theologians joined the debate, pondering the deeper meaning of humanity's tiny emissary encountering such cosmic fury. What did it say about our place in the universe if Voyager 2, launched with hopes of humble exploration, had become the herald of a cosmic revelation too large for human comprehension? Some mused that the discovery might herald a new epoch in human understanding, force us to confront limits of knowledge and courage. Others whispered of existential threat, a warning from the cosmos that intelligence must tread lightly or risk unleashing forces beyond control. Meanwhile, mission controllers faced a dilemma of protocol. Voyager 2's trajectory could not be altered, and its instruments would record every surge until power failures silenced its transmitter. Data budgets were reallocated, deprioritizing other deep space missions to secure every possible byte of information. Late-night shifts were extended. Scientists work around the clock, decoding the streams, translating cryptic spikes into meaningful curves. Every anomaly was charted, every fluctuation mapped, as if piecing together a puzzle whose final image might reveal the fate of worlds. Beyond the technical hurdles lay the heart of the mystery. Why now? Voyager 2 had crossed the helipause in 2018, cruising through the interstellar medium for years without so much as a hint of cosmic upheaval. Then suddenly, at a distance exceeding 124 astronomical units, this terrifying phenomenon emerged from the silence. Was the spacecraft merely drifting into a denser region of exotic plasma? Or had something dynamic stirred the cosmic soup? Perhaps an interstellar shock front, the aftermath of a distant supernova, was finally washing over our corner of the galaxy. Radio telescopes listened for complementary signals, detecting faint echoes, but nothing on the scale of what Voyager 2 recorded. Particle detectors on the International Space Station and in lunar orbit searched for correlated bursts, but their readings remained within expected solar cycle variations. Only Voyager 2, isolated and drifting, bore witness to the source's true ferocity. It was as if the encounter was unique to its path, an accidental rendezvous with a cosmic phenomenon no other probe was privy to. By then, the public had caught wind of the mystery. Headlines proclaimed a cosmic threat. Talk shows speculated about alien contact or impending doom. Social media buzzed with theories from dystopian warnings of Earth's obliteration to utopian dreams of first contact. Conspiracy theorists claimed governments were hiding the truth, while scientific skeptics urged caution, reminding everyone of past false alarms. Yet, the data lay unblinking in the archives. And the more it was examined, the more its terrifying nature became undeniable. For the scientific community, the priority was clear. Decode the pattern. If the modulation hinted at structure and purpose, deciphering it might unlock new realms of physics or establish contact with unknown intelligences. Teams of mathematicians, linguists, and cryptographers joined forces, treating the cosmic oscillations like a Rosetta Stone from the stars. Algorithms were trained to recognize repeating motifs. Neural networks scoured the time series for hidden messages. Every possible angle was pursued in hopes of translating the deadliest whisper of interstellar depth into human language. But the more effort poured into interpretation, the more questions multiplied. Was the modulation constant or evolving? Did it possess a syntax, a grammar of cosmic signals? Or was it a chaotic artifact of a natural phenomenon too complex for random chance to produce, yet devoid of intention? The balance between awe and terror hung on the outcome. A true signal of extraterrestrial mind would forever reshape human destiny. A natural anomaly of this magnitude would rewrite physics textbooks and raise urgent concerns about the stability of interstellar space. Beyond intellectual pursuit lay the practical. If the phenomenon indicated a growing wave of high-energy particles, Earth's technological infrastructure could be at risk. Satellites, power grids, communication networks, each vulnerable to charged particle storms. Precautionary measures would need to be considered, ranging from deepening fault tolerances to hunting for shielding solutions. The discovery was not merely academic. It carried urgent ramifications for modern civilization's fragile web of technology. Yet, the greatest unease came from the unknown. Voyager 2 was alone, long past any opportunity for physical intervention. If the phenomenon signaled an advancing front of cosmic turbulence, No spacecraft could intercept or divert it. Humanity could only watch. Instruments pointed skyward, praying that Earth's magnetic cocoon would hold the knowledge that our planet floats within the same cosmic sea of charged currents once thought gentle, now filled with hidden storms, was enough to make even the most rational mind shudder. As sessions of global scientific councils convened via secure channels, strategies formed to cope with the potential worst-case scenarios. Data from Voyager 2 would guide forecasts of particle flux through the solar system. Models previously used for predicting solar storms had to be expanded to account for interstellar disturbances. Agencies once focused on Mars rovers and asteroid defense found themselves grappling with the urgent threat of cosmic radiation. It was a humbling pivot from exploration brochures to crisis management in the face of cosmic unknowns. In the halls of universities, students marveled at the speed with which a single spacecraft could disrupt centuries of complacency. Research proposals poured in, conferences scheduled, funding agencies scrambled to allocate resources. The event had shattered the illusion that space beyond the heliosphere was a tranquil expanse. It revealed instead a dynamic, potentially hostile frontier where human ingenuity was still in its infancy. The knowledge that Voyager 2's instruments had recorded this storm before anything else meant the mission's legacy was no longer just exploration, but a warning beacon. Public interest surged. Documentaries were greenlit. Podcasts multiplied. Classrooms buzzed with excitement and dread. Yet, amid the hype, a more profound shift took root. Collective consciousness, long distracted by terrestrial quarrels, turned its gaze outward. Questions of survival, unity, and responsibility echoed in halls of power and living rooms alike. If the universe could launch a threat so grand and unexpected, what did that mean for humanity's future among the stars? Amid this global reawakening, Voyager 2 continued its silent vigil. Its faded gold record, a relic of hopeful greetings, had become uplifted in ironic contrast to the menacing signals it now intercepted. The probe's fragile decades-old systems remained in operation, dutifully beaming home each terrifying revelation. There would come a time when power levels dropped, when antennas fell silent. Until that final transmission, Voyager 2 would stand as both explorer and sentinel, a lone ambassador, charting the boundary between human knowledge and the dark unknown. Every byte of data it sent further illustrated the depth of the mystery. Particle densities, magnetic field vectors, plasma wave spectrograms, all painting a picture of interstellar space stirred by forces beyond prior comprehension. Each data set raised more questions than it answered. What was the true nature of the engine driving these bursts? Could it be harnessed or mitigated? Was it a singular event or part of a grander galactic cycle? The implications reached from scientific laboratories to geopolitical strategies, from metaphysical introspection to the practical need for planetary defense. Voyager 2's terrifying discovery forced humanity to reckon with its vulnerability and insignificance. Our species, perched on a small world bathed in sunlight, suddenly found itself at the mercy of a cosmic tempest whose origins lay far beyond our grasp. And yet, in that revelation, there shone a spark of determination. If the universe held threats so vast, we must rise to meet them through ingenuity, unity, and an unquenchable thirst for knowledge. For in confronting the darkness, Voyager 2 had not only exposed a terrifying truth, but also ignited the flame of human resolve to venture ever onward into the unknown. As the data streams continued to flow, an intricate ballet unfolded between human ingenuity and cosmic mystery. Laboratories devoted to plasma physics found themselves racing against time, repurposing accelerators and magnetic confinement devices to recreate on a miniature scale the ferocious conditions indicated by Voyager 2's sensors. Physicists experimented with high-power lasers striking dense targets, seeking laboratory analogs for the particle bursts. Each experiment refined our understanding of how charged particles gained such staggering energies, but none fully captured the sheer scale reported by the probe. Even so, every incremental insight brought a measure of control, a slender promise that the chaos might one day be tamed, or at least anticipated. Meanwhile, space agencies across the globe entered an unprecedented era of cooperation. Historically, the exploration of the outer solar system had seen isolated efforts and occasional rivalry. But the Voyager anomaly transcended borders. Engineers in Europe collaborated with counterparts in Asia to co-develop next-generation detectors capable of distinguishing the subtle modulations in particle flux. South American observatories recalibrated their telescopes to hunt for optical counterparts, while African research institutes contributed critical theoretical models rooted in decades of cosmic ray studies. A single-page memorandum drafted in multiple languages formalized the Interstellar Emergency Coalition, a body as agile as it was comprehensive, tasked with coordinating observations, sharing data in real time, and advising governments on protective measures. On the ground, power providers looked skyward with a mixture of fascination and concern. Engineers in North America and Europe simulated grid responses to extreme cosmic ray bombardment, discovering that modern high-voltage transformers stood vulnerable to cumulative damage. A coalition of electrical utilities began crafting contingency protocols. Power plants would stand by to isolate key transmission lines. Distributed energy resources, rooftop solar installations, and neighborhood battery banks would be configured to sustain essential services. Technical conferences buzzed with panels debating whether early warning systems could integrate Voyager 2's particle flux readings, effectively giving Earth a meteorological forecast of cosmic radiation storms. Satellite operators, too, felt the shifting winds. Geostationary and low Earth orbit constellations, increasingly critical for communications, navigation, and Earth observation, risked malfunctions when bombarded by energetic particles. Satellite designers accelerated work on hardened electronics, embedding redundant circuits and advanced error-correcting codes to ensure data integrity in the face of unprecedented radiation levels. While a full prevention of single-event upsets remained out of reach, the industry rallied to push next-generation satellite buses through expedited design reviews and launch schedules. In mission control rooms, panels displayed real-time maps of charged particle densities across orbital altitudes, feeding models that would eventually become standard practice in spacecraft design. Yet, not all responses were technical. Cultural institutions recognized that humanity faced a moment of profound collective uncertainty. Museums curated exhibitions tracing the journey of the Voyager probes, pairing the Golden Record's hopeful greeting with the stark revelation of cosmic fury. Art galleries commissioned immersive installations, blending soundscapes derived from the particle data with visual abstractions of interstellar turbulence. Composers translated the oscillation patterns into haunting symphonies, their crescendos echoing the terrifying bursts recorded by the probe. Writers penned speculative fiction that grafted the emotional landscape of a species grappling with forces far beyond its control, while philosophers held public debates on what it meant to confront an intelligence or a force capable of wielding energies that dwarf human technology. Education systems seized the moment to inspire a new generation. Science curricula incorporated modules on interstellar medium physics, cosmic rays, and the history of robotic exploration. Students built scaled models of particle detectors using simple components, learning firsthand the challenges of capturing and interpreting high-energy events. Video conferences linked classrooms from Cairo to Buenos Aires, allowing pupils to pose questions to mission scientists and share their homemade experiments. Suddenly, complex astrophysical processes leapt off the chalkboard and into living rooms, kindling curiosity and a shared sense of urgency to understand and protect the home world. Politicians found themselves debating budgets and international accords with a new moral imperative. Defense committees, long focused on terrestrial threats, convened to establish protocols for a galactic threat response. Diplomatic envoys drafted treaties ensuring that data gleaned from Voyager 2's anomaly would remain openly shared, free from national security restrictions. Leaders weighed the allocation of resources between Earthbound concerns and the unpredictable safety challenges posed by interstellar radiation. Parliaments across continents heard impassioned speeches. Some warned that humanity's preoccupation with distant cosmic storms risked neglecting immediate crisis, while others argued that if the universe could so easily unleash destructive power, then our civilization had a moral duty to prepare for all eventualities. Private industry, too, sees the potential for innovation. Companies specializing in radiation shielding began developing advanced composites infused with hydrogen-rich polymers and carbon nanotubes, seeking to create lightweight panels capable of protecting not only spacecraft electronics, but also future crewed vessels venturing beyond Earth's magnetosphere. Biotechnology firms explored genetically engineered proteins that might repair radiation damage in living cells, anticipating the day when astronauts would confront harsher cosmic environments. Investments poured into defense contractors proposing early warning sensor networks that combined ground-based detectors with small satellites in interplanetary orbit, forming a planetary shield reminiscent of science fiction constructs once thought purely imaginary. In this clamorous flurry of activity, one group worked quietly but urgently: the communication specialists. They labored to compress, encode, and transmit every precious packet of Voyager 2's data back to Earth. The Deep Space Network, that venerable array of giant dish antennas, underwent schedule overhauls and software updates to handle the surge. Operators in Madrid, Goldstone, and Canberra synchronized their efforts, maximizing the probe's limited transmit window as it rotated to face our direction. Each successful transmission was greeted with relief, as though the fragile silver cylinder drifting on the edge of the solar system had whispered a secret that only collective human resolve could catch. By mid-year, patterns began to emerge in the long-term data. The bursts of particles displayed a subtle periodicity tied to Voyager 2's orientation with respect to the galactic magnetic field. Advanced maps of the local interstellar medium hinted at structures, filaments of high-density plasma threaded by magnetic lines so twisted that they funneled charged particles like cosmic riverbanks. Computational fluid dynamic simulations of the interstellar wind showed shock fronts corralling streams of ions, amplifying their energies to the levels observed. Although still daunting, the phenomenon could at last be framed within the laws of magnetohydrodynamics. It was no longer an inexplicable anomaly, but a grand natural spectacle, albeit one of terrifying might. However, the modulation superimposed on the particle data remained mysterious. Statistical analyses uncovered features reminiscent of prime number sequences, fractal dimensionality, and patterns that defied purely stochastic origins. Was this simply the fingerprint of turbulent plasma waves interacting in mathematically complex but deterministic ways? Or was there something deeper? Could the coupling of interstellar plasma with relic magnetic fields, perhaps left over from long-gone supernovae, imprint such quasi-regular signatures? The leading theory, tentatively dubbed the galactic dynamo hypothesis, posited that ancient stellar explosions had seeded the region with magnetized turbulence that only now, decades after Voyager 2's passing through the helipause, was releasing pent-up energy and cyclical surges. This hypothesis gave hope for prediction. If the cycle could be characterized, then peak events, those capable of straining Earth's magnetosphere, could be forecast months in advance. Models incorporated galaxy-scale simulations accounting for the mass distribution of stars, interstellar dust clouds, and the motion of dark matter. Though these models stretched computational resources to their limits, the prospect of anticipating cosmic radiations spurred further investment in supercomputing. A new discipline emerged at the intersection of astrophysics, space weather forecasting, and planetary defense. Interstellar meteorology, complete with its own journals, conferences, and professional societies. Yet, even as models advanced, the human toll of constant vigilance weighed on mission personnel. Control room rotations grew punishing. Scientists who once dreamed of leisurely nights spent pondering the secrets of the universe now woke at all hours to monitor data spikes that might indicate the next crescendo of radiation. Psychological support networks were established to help them manage stress. Recognizing that the weight of cosmic uncertainty could take a heavy emotional price, virtual reality programs offered simulated retreats, transporting weary analysts to serene alien landscapes or tranquil terrestrial vistas, providing brief respite from the unceasing flow of cosmic data. Public psychology, too, swung between fascination and fatigue. At first, every astronomer's tweet, every press release sent waves of excitement through social media. But as months passed with relentless updates, citizen interest wavered. To sustain engagement, educators and communicators crafted narrative threads that connected the cosmic storm to human stories. They highlighted engineers designing hardened electronics in workshops at universities, showed families installing backyard cosmic ray detectors, and profiled the unsung librarians cataloging terabytes of spectral archives. The story of Voyager 2's discovery became more than a tale of scientific wonder. It became a tapestry woven from countless human endeavors, each thread reinforcing the others. In boardrooms and policy circles, the anomaly prompted a reevaluation of long-term space exploration goals. Plans for human missions to Mars and beyond now had to contend with the reality that the interplanetary medium could turn from benign to hostile without notice. Shielded habitats, deep underground laboratories on the moon, and potentially even-generation ships designed with integrated radiation sinks moved from science fiction tropes to essential mission architecture. Funding agencies opened calls for proposals to develop self-healing materials, dynamic field generators to deflect charged particles, and real-time dormitory suits for astronauts. At the same time, the unexpected boon of intellectual collaboration bridged divides. Rival states found common cause in facing a cosmic challenge. Joint ventures formed to develop next-generation deep space probes equipped with advanced technology inspired by lessons from Voyager 2. These spacecraft would carry multiple detectors calibrated to the same standards, ensuring that no single anomaly could go unverified. Launch windows were being eyed not merely for planetary alignment, but for optimal sampling of interstellar phenomena. Teams preparing these missions recognized that they too might become early warning nodes for cosmic storms, extending humanity's protective reach deep into the void. On a philosophical plane, the encounter with raw cosmic power provoked existential contemplation. Thinkers pondered the nature of unpredictability at galactic scales and wondered if a supreme intelligence could ever hope to master such forces. Some interpreted the rhythmic modulation as an invitation to humility, a reminder that the universe's grandeur outstrips even our loftiest technological achievements. Others saw it as a call to transcend limits, to forge partnerships between biology and machine, between art and science that could one day navigate safely through space's hidden perils. Perhaps the modulation was not malevolent, but a cosmic heartbeat, a testament to the dynamic life of the interstellar medium itself. In art studios around the world, creators sought to embody the newfound understanding. Sculptors crafted interactive installations that pulsed with lights driven by authentic Voyager 2 data, inviting viewers to step inside simulated shock fronts. Digital artists produced virtual voyages along magnetic filaments, illustrating how particles could travel unimaginable distances before bursting with renewed energy. Dancers choreographed performances replicating the ebb and flow of cosmic currents, their movements guided by the statistical profiles of the data. Through these expressions, the enigmatic discovery transcended the realm of raw information and entered the collective human consciousness as both wonder and caution. Amid all these endeavors, Voyager 2 continued its lonely journey, its nuclear power source slowly dwindling, but still sufficient to fuel its instruments. Engineers projected that by the late 2020s, The spacecraft would enter a twilight phase with only minimal telemetry trickling back. Yet every gram of plutonium in its power cells felt laden with the hopes of a species striving to understand its cosmic environment. Plans were drawn for a successor, a fleet of small probes. Each an agile node worked across vast distances, ready to sample and relay the conditions of the interstellar frontier. These probes would be cheaper, faster to build, and carry lessons learned from Voyager 2's trials, embodying humanity's determination to not be caught unawares by the universe's hidden storms. The ripple effects of Voyager 2's terrifying revelation reached even the deepest reaches of cultural narrative. Myths and legends once bound to earthly phenomena began incorporating motifs of cosmic turbulence. Storytellers would new creation epics in which the heavens themselves labored and threatened only to be tamed by heroes of intellect and unity. Religions contemplated cosmic stewardship, teaching that care for our planet extended to understanding and respecting the broader environment of space. Interdisciplinary dialogues flourished, uniting scholars of theology, science, and the arts in quest to interpret the significance of an ever-shifting cosmos. Through it all, one truth emerged. Humanity's journey beyond the cradle of Earth was not merely a technical challenge, but a profound evolution of collective consciousness. Confronted with forces that could tear apart the very fabric of our planetary protection, we responded not with despair, but with collaboration, creativity, and courage. Each instrument recalibrated, each treaty signed, each symposium held became part of a grand human tapestry stretching across the globe.